Hello, honors pre-calculus students. This is Mr. Gonzago, and the learning target here is to graph rational functions without a graphing calculator. So if you look at example number 1, the first thing you should notice is the x plus 4's are in common, and they're going to completely reduce out. So there's a point of discontinuity when x is negative 4. So here in red, I'm writing the reduced rational function. So the first thing you should notice is there's a point of discontinuity at negative 4, and to calculate the y value, we need to plug negative 4 into the reduced expression, into that red equation. So when you do that, you're going to get 3 times 81 over, when you plug in negative 4, you're going to get 8, and when you square it, you get 64. So you get 243 over 64. The point of discontinuity is 243 over 64. If you use your calculator just for computational purposes, this decimal is around 3.8. So it's approximately 3.8. All right. We're going to find the limit as x goes to infinity of f of x. That'll give us the horizontal asymptote. So looking at f of x, if you were to multiply that out, you're going to get 3x cubed over x cubed, and that's going to go to 3. So that means the horizontal asymptote is y equal 3. Next thing you should notice is the x-intercept is 5 when the numerator is 0. You should recognize that there is a vertical asymptote at x equals 4, so I'm just going to draw that in. So x equal 4 is the vertical asymptote, and then there's a horizontal asymptote at y equal 3. Draw that in. We have the point of discontinuity at negative 4, 3.8. So negative 4, 3.8. So that's a little above that asymptote. We need to calculate the y-intercept. So f of 0 is going to be 3 times 25. I like to plug into the reduced. It makes the number smaller, over 16. So 75 over 16, and 75 over 16 is approximately 4.7. So the y-intercept is around 4.7. Right, so now we have the sketch. Since this is an even exponent on the x minus 5, it just touches. And since it is an even exponent on the x minus 4, the direction is the same. So the graph has no choice but to start, bounce over that point of discontinuity, hit the y-intercept, and approach that vertical asymptote. Since it's even, it's going to stay in the same direction. It's going to come down. It's going to touch that x-intercept and bounce back up towards that horizontal asymptote. Remember, you can cross horizontal asymptotes. Horizontal asymptotes are the end behavior. So there's the function, or the graph of the function for problem number 1. Hello, honors pre-calculus students. Here's problem number 2. First thing I hope you recognize is there's an x plus 5 and an x plus 5 squared. So when you reduce this, you get negative 4, x plus 3, x minus 1 squared, over x plus 5, x minus 3 squared, x plus 4. So since there is still an x plus 5 in the denominator, there is a vertical asymptote at x equal 5. So the vertical asymptotes for this problem are going to be x equal 5, x equals 3, excuse me, that's x equals negative 5, x equal 3, and x equals -4. To find the horizontal asymptote, we're going to send x to infinity for the function. If you look at the reduced or the non-reduced, it really doesn't matter. If you look at the reduced, you're going to get -4x cubed in some other terms, divided by x to the 4th, plus some other terms. So the limit here will be 0. So that means the horizontal asymptote is on top of the x-axis, or y equals 0. Okay. We know the x-intercepts, looking at the numerator, are at -3 and +1. We know the graph just touches at x equals 1 and goes through the x equals -3. For the y-intercept, we're going to calculate f of 0. So I like to plug into the reduced, so -4 times 3 times 1 over 5 times 9 times 4. So I could reduce that, so -4 reduces, so the 3 reduces with the 9 3 times, 4 goes in the 4 once, so it looks like we have -1 over 15. So that's a small y-intercept. So I'll just put a dot right there. There was no point of discontinuity, but there was that vertical asymptote. So let's draw this graph. We talked about in class how to sketch this graph, but if you're not sure where the graph would start, you can find the limit as x approaches -4 from the right of f of x. If you're not sure where the graph starts, you can use the left and right limits. So as x approaches -4 from the right, so you're plugging in like -3.99999. So I'm going to write that down. -0.3999. So you have -4 times a negative times a positive when you square it times a positive divided by a positive, another positive, and when you plug in -3.999 plus 4, you have a small positive. So when you look at these, you have two negatives and divided by a small, so this is going to go to positive infinity. So the graph must start up here on the right-hand side of -4. It goes through that y-intercept. Eventually it has to turn around, hit that, goes through the x-intercept, turn around, hit the y-intercept. Then at the 1, it just touches and goes back down. That's the only option in that middle section. Now around x equals 3, we have an even exponent. So the graph must start down at the bottom and go up towards that horizontal asymptote. Remember, you cannot create x-intercepts. To the left of -4, the exponent here in yellow is 1, so it has to start down at the bottom. I'm not sure how high it goes up, but it can't cross that x-axis, so it's going to eventually turn back around and approach the other vertical asymptote on the right-hand side. And then the x plus 5, remember we talked about using the reduced fraction. So the exponent there is 1. Since we're starting down on the right-hand side, we have to start at the top when you're a little bit to the left of -5. So the graph has to look like the following. Let's look at the next problem. Okay, the last problem I like to draw is number 3 here. When you look at this, you got an x minus 3 squared in the numerator, x minus 3 in the denominator. So this reduces to 2 times x plus 3, x minus 3 over x minus 2 squared. So as we discussed in class, there is a point of discontinuity at 3, 0. Since there is a factor left in the numerator, there's a point of discontinuity at 3, 0. I'm going to put an open circle there right away. The other x-intercept is at x equals negative 3. If I want to calculate the y-intercept, f of 0, so 2 times 3 times negative 3 over 4. That's going to be negative 9 over 2. This is negative 4.5. So put the y-intercept there. The vertical asymptote is x equals 2. Get that from the denominator. The horizontal asymptote, when you send x to infinity, so the limit as x goes to infinity of f of x. If you're to multiply the reduced fraction, it's going to be 2x squared plus some other terms, divided by x squared plus some other terms. So the limit as x goes to infinity is 2, which means the horizontal asymptote is y equals 2. So I have the skeleton. I know it goes through the x equals negative 3. It has to start then over here. Goes through that x-intercept, goes through the y-intercept, and approaches the vertical asymptote. Since the asymptote has a multiplicity of 2, it starts in the same direction. So it starts down at the bottom, goes up, jumps over that point of discontinuity, and approaches that horizontal asymptote. So I'm hoping that you found this video on graphing rational functions helpful. You always could find the limit as x approaches 2 from the right, and the limit as x approaches 2 from the left, if you're not sure how to graph a function. If you're to plug a number a little bigger than 2 into that reduced fraction, you will get negative infinity. And I'm going to do it over here. So you got 2 times a positive times a negative over a small negative. You're plugging in like 2.00001. If you find the limit as x approaches 2 from the left, like you're plugging in 1.99999, that also is negative infinity. I'll do that over here. So you got 2 times a positive times a negative. When you plug in 1.999 minus 2 and square it, you get a small positive. So that's why that goes to infinity. So I'm hoping you found this useful.